Day 50, Honors Physics, Conservation of Momentum, Problem 16. This also has an element of conservation of energy, which is where you need to start this problem, over here on the left. I'm showing you the ball, the golf ball. I have a poor golf ball. This is my golf ball here. Starting at a certain height of 3 meters, it comes down, transfers this energy to kinetic energy, and we're assuming no loss of energy on the way down, no loss of mechanical energy on the way down. So on the way down, there'll be conservation of energy. The GPE at the top will equal the kinetic energy at the bottom. So if you do the calculation there, set mgh1 equal to 1/2 mv squared, and the black dots here mean you show the work. You show me the work there. And interestingly enough, if you look at this carefully, the masses really don't matter. You can cancel those out. You don't need to use them if there is no loss of energy, in this particular case at least. So V1, the velocity with which it strikes the ground is 7.67 meters per second. And likewise, you do the same thing in reverse on the way back up. There's conservation of energy. The kinetic energy transfers into GPE2, so those are equal to each other. Do the same calculation. Once again, the masses cancel out. You would show work in this slot right here, and then you get the V2, the velocity coming off the floor of 6.71. So then what we do is figure out the momentum going into the floor. Just before the ball hits the floor, you take the mass of the ball. Now you do need the mass for sure, times the velocity going into the floor, so we have the momentum going towards the floor, and then the momentum coming off the floor. The key, however, in this problem is what is delta P? And you got to be a little bit careful here because, as I mentioned in class, you have delta P and you have total momentum. Here we're not doing a direct application of conservation of momentum. We're just looking for the relationship between impulse and change in momentum, which are equal to each other. Those are the two basic types of new problems we're having here. This is an impulse problem, so we're looking for the change in momentum. Now, if a ball is going down and then reverses direction and goes up, we would have to call one of those directions negative. You can call the down direction negative, so the original number is negative 3.45, and then the final momentum is 0.302 up, and if you subtract those two, that's the change. In other words, the change is going to be, essentially, it's going to look like you're adding the two numbers. If you want to do it mathematically, it technically would be, if you want to put the negatives in there, which tend to sometimes complicate the problem, it would be something like 0.302 as your positive momentum upward, minus the negative 0.345, that was the original downward momentum, because change in anything is the final minus the initial, P sub 2 minus P sub 1. So your delta P is 0.647 kilograms meters per second. And I was consistent with all those units all the way along. I double-checked those before I started. I made sure I put the mass in kilograms, so therefore that's my delta P. And that's my momentum then. So that's the answer to part A, actually, right there. Change of momentum is the impulse. So, well, I guess I went up here. So impulse, J equals 0.0647. That's my answer. Now in part B, it says to find the energy dissipated. So I'm kind of numbering my steps here, 1, 2, 3, 4. I'm not going to do this part totally, but what you would do is you would get the KE1 as the ball enters the floor, and here you do need to use the mass, so 1/2 times 0.045, make sure it's kilograms, times the velocity as it impacts the floor, 7.67 squared. That will be your KE1. The initial kinetic energy before it hits the floor. You do the same thing for KE2, the kinetic energy coming off the floor. You'll get a value for these two numbers. Velocity coming off the floor is 6.71 meters per second squared. And simply all you would do is calculate those two values and subtract. The first value, KE1, will be bigger. Subtract those two, and that will give you the energy dissipated, basically transferred to heat, during the impact. because this is an inelastic collision. Well, there's some elasticity to it, because it's a pretty good bounce, but there will be some loss of kinetic energy, so it's not a perfectly elastic collision.